So in the last lecture, what we finished off with was discussing how oxygen moves from the air in the alveoli into the blood plasma within the pulmonary capillaries. And we acknowledged that the partial pressure of oxygen within the air in the alveoli is 100 millimeters of mercury. And the partial pressure of oxygen within the blood plasma within the pulmonary capillaries, specifically deoxygenated blood, by the way, is 40 millimeters of mercury. Okay? So there's what's called a partial pressure gradient here for oxygen. The partial pressure of oxygen within the air in the alveoli is 100, and the partial pressure of oxygen within the blood plasma in the pulmonary capillaries is 40. So oxygen wants to move down this partial pressure gradient, and it wants to move into the blood plasma, and it does. And very quickly, it drives the partial pressure of oxygen within the blood plasma up to 100. We don't need to get into all of this again, but very little oxygen actually needs to come from the air in the alveoli into the blood plasma in order to drive the partial pressure of oxygen within the blood plasma up to 100. Why? Because the oxygen is nonpolar and the plasma, which is water mostly, is very polar. They don't exist together very well, so you don't actually need very many oxygen molecules to move into the blood plasma to drive the partial pressure of oxygen within that blood plasma up to 100, because the oxygen is nonpolar, the blood plasma is made up of water, which is very polar, so the oxygen bounces around like crazy, and you only need a very small amount of oxygen molecules to actually move into the blood plasma, the water, to bounce around enough to drive the partial pressure of oxygen within the blood plasma up to 100. So now, the partial pressure of oxygen within the air in the alveoli and the blood plasma are both 100. So little oxygen actually has left the air in the alveoli into the blood that the partial pressure of oxygen within the air didn't decrease at all. Okay, so you get into this very real question here of what was the point of driving the partial pressure of oxygen within the blood plasma up to 100, right? Because so little oxygen has actually moved from the air in the alveoli into the bloodstream. So little oxygen actually needed to come into the blood plasma to drive the partial pressure of oxygen within the blood plasma up to 100. What's the point of doing this at all? And the answer is, well, it's the second component of the blood. We need to look at what are called the erythrocytes, or the red blood cells, and specifically a protein within these red blood cells called hemoglobin. Because what's going to happen here is changing the partial pressure of oxygen within the blood plasma is going to influence the red blood cells. Okay. Blood is made up of, it's not perfectly 50-50, but it's about half blood plasma and half red blood cells. So when you talk about blood, you're talking about the plasma and the red blood cells. All we've spoken about so far is driving the partial pressure of oxygen within the blood plasma, the watery component of the blood, up to 100. And now what we need to do is look at how changing the partial pressure of oxygen within the blood plasma influences the other component of the blood called the red blood cells, or these erythrocytes. Okay, there's actually a third component of the blood, which is the buffy coat, which is immune cells, but that's not something that we're talking about here, and it makes up a very small percentage of the actual blood itself. Blood is mostly blood plasma and red blood cells. So what's going to happen here? So let's first off talk about some basic anatomy of a red blood cell. Okay, it's a cell. Okay, so it has a plasma membrane. Okay. Each red blood cell is a cell. It has a plasma membrane. In order for something to be a cell, it has to have a plasma membrane. And then what exists inside of these red blood cells, of these erythrocytes, as they're called? Well, there's this protein within these red blood cells called hemoglobin. And what hemoglobin does, each hemoglobin protein, each one of these is one hemoglobin protein. Each one of these hemoglobin proteins is capable of binding 4 oxygens. 1, 2, 3, 4. 1, 2, 3, 4. Right? So inside of red blood cells, erythrocytes, there's hemoglobin. And each hemoglobin can bind 4 oxygen molecules. Now the question is, how much oxygen is actually bound to hemoglobin within the red blood cells? So let's give you some numbers here, first of all, because it's pretty amazing. Okay, this varies to some degree from one person to the next, but there's about 25 trillion red blood cells in a given person's bloodstream. Okay, 25 trillion. Absolutely mind-blowing. And to take that a step further, within every one of the 25 trillion red blood cells in the human body, within every red blood cell, there's estimated to be about 250 million molecules of hemoglobin. And each one of those hemoglobin proteins can bind 4 oxygen molecules. So think about that. Throughout the body, there are 25 trillion red blood cells, or erythrocytes as they're called. And within every one of those 25 trillion red blood cells, there's something like 250 million hemoglobin proteins, each capable of binding 4 oxygen molecules. The oxygen carrying capacity of the human body is incredible. Now, the question, yet again, is always going to come back to how much of the hemoglobin within the red blood cells has oxygen bound to it. We call this the hemoglobin saturation. How saturated is hemoglobin with oxygen is the question. Okay, you look at all of the hemoglobin proteins within a red blood cell, and then you see how much oxygen is bound to those hemoglobin proteins. How saturated are those hemoglobin proteins with oxygen? So in the first, red blood cell here on the right, hemoglobin is 75% saturated. That means of the 250 million hemoglobin molecules, I shouldn't call them molecules, of the 250 million hemoglobin proteins within this red blood cell, cumulatively, those hemoglobin proteins are about 75% saturated with oxygen. Now, on average, what that would mean is that the hemoglobin proteins have 3 out of 4 oxygen molecules bound to them, right? Because every hemoglobin protein is capable of binding 4 oxygen molecules. And if hemoglobin is 75% saturated, that means every hemoglobin protein is binding 3 oxygen molecules and isn't binding a 4th, right? 3 out of 4 oxygen molecules are bound to hemoglobin, and it's missing the 4th one. Now, that's not literally going to be true for every single hemoglobin protein throughout the erythrocyte, but the 75% saturated means that cumulatively throughout the red blood cell, hemoglobin is about 75% saturated with oxygen. It could be more saturated with oxygen is the point that it's trying to make. Okay, now over here on the left, hemoglobin is about 100% saturated with oxygen. Okay, it doesn't really ever happen in the human body. It can get up to like 98, 99%. We don't see 100% saturation, and that's due to a magnitude of reasons that we're not going to discuss in this class. But basically, what this implies is that if you looked at a red blood cell and you said the red blood cell is 100% saturated with oxygen, that would mean the hemoglobin proteins inside, more or less all of them, have 4 molecules of oxygen bound to them, right? Because each hemoglobin protein is capable of binding 4 oxygens, 4 molecules of oxygen, and if every hemoglobin protein inside of the red blood cell has 4 oxygen molecules bound to it, then hemoglobin is approximately 100% saturated within the red blood cell. Another way of saying that is the oxygen carrying capacity of the red blood cell would be maxed out, right? The red blood cell would be carrying as much oxygen as it possibly can if all of the hemoglobin inside of it was 100% saturated with oxygen. Now, the one on the right over here, this red blood cell has the ability to improve its oxygen carrying capacity, right? If these hemoglobin proteins within it would start binding that fourth oxygen, because right now all the hemoglobin proteins on average are binding about 3 oxygen molecules. If they could all start binding that fourth one, then this red blood cell would significantly improve by 25% its oxygen carrying capacity. So now what you have to do is you have to take this into consideration as you're talking about the blood that's traveling past the alveoli. You have to ask yourself, how saturated are the red blood cells with oxygen? And by that, what it's saying is, how saturated are the hemoglobin proteins within the red blood cells with oxygen? Let's give an example. Okay, so these red blood cells that exist within what's called deoxygenated blood, right? That deoxygenated blood is traveling through this pulmonary capillary past this alveolus right here. Okay, now these red blood cells, each of them are about 75% saturated with oxygen, meaning the hemoglobin within them is about 75% saturated, right? 75% saturated. So these red blood cells are only at 75% of their oxygen carrying capacity. These red blood cells are by a fourth capable of improving their oxygen carrying capacity. Now we'll get into all of this, but within deoxygenated blood, right, that blood that's coming from the right ventricle into the pulmonary arteries, pulmonary arterioles, and then pulmonary capillaries here, that deoxygenated blood, the red blood cells within it are about 75% saturated with oxygen. The hemoglobin within them is about 75% saturated with oxygen. Now, the red blood, the blood plasma, you also know, has a partial pressure of oxygen of 40. Okay? And then what happens? Well, oxygen moves from the alveoli into the blood plasma. I'm saying that intentionally. The oxygen is moving from the alveoli into the blood plasma due to this partial pressure gradient. That drives the partial pressure of oxygen within the blood plasma up to 100. Right? But very, very, very little oxygen has actually come into the blood plasma, into the watery component of the blood. But what this is going to do is it's going to have an influence over the red blood cells within the blood as well. Okay, and how? That becomes the question. So the first point I need to make is that if the partial pressure of oxygen within the blood plasma were to be 40, for example, this is true with deoxygenated blood, then the partial pressure of oxygen within the intracellular fluid of the red blood cells, they're cells, right? So they have intracellular fluid, they have a cytosol. The partial pressure of oxygen within the intracellular fluid, the cytosol, would also be approximately 40, because oxygen is incredibly nonpolar. It can just rip right through the plasma membranes of any cell. Okay, so what's happening here is if the partial pressure of oxygen within the blood plasma, the watery component of the blood that surrounds the red blood cells, if the partial pressure of oxygen within the blood plasma is 40, then the partial pressure of oxygen within the intracellular fluid, the cytosol of the red blood cells, is also 40. It's just logical. It has to be. And maybe you would think, well, wouldn't the partial pressure of oxygen within the red blood cells actually be less because they're consuming oxygen because they're cells? And then the answer actually is no. Red blood cells they lack mitochondria. This leads into a whole separate conversation, but they don't actually consume the oxygen that exists within them. They don't have mitochondria in order to do so. It's necessary that that be true. So whatever the partial pressure is within the blood plasma that surrounds the red blood cells, that's going to be the same partial pressure of oxygen that exists inside of the red blood cell itself. And this leads us to a curve that tends to confuse a lot of people, which is called the Oxygen-Hemoglobin Dissociation curve. Now, What is it showing? Well, first of all, on the x-axis, what is being displayed is the partial pressure of oxygen within the blood plasma, or the intracellular fluid of the red blood cells, because ultimately that's exactly the same. So call it whatever you want. It's the partial pressure of oxygen. That's what's being displayed. But I can tell you, what it means is it's the partial pressure of oxygen within the blood plasma and thus within the red blood cells. Okay, could be 0, 20, 40, 60, 80, 100. Okay, could be even higher than 100, although that's relatively rare. All right, what about the y-axis? That is the saturation rate of the red blood cells, specifically hemoglobin within the red blood cells. So we know that red blood cells, specifically the hemoglobin within the red blood cells, is, it has a certain saturation rate with oxygen, right? The hemoglobin proteins within a red blood cell could be 20, 40, 60, 80, 100% saturated with oxygen. That is what exists on the y-axis. So what the oxygen-hemoglobin dissociation curve does is it shows you on the x-axis, you're looking at the partial pressure of oxygen within the blood plasma and thus the intracellular fluid of the red blood cells, right? That could be, in our example, from 0 to 100. From 0 to 100 millimeters of mercury. And on the y-axis, what the oxygen-hemoglobin dissociation curve is showing you is it is showing you how saturated the hemoglobin proteins are inside of the red blood cells with oxygen. That could range from 0 to 100% saturated. This all sounds very confusing, but it's actually not. So ask yourself this. Okay, here is an alveolus. Here is a pulmonary capillary. Okay, right here, traveling through the pulmonary capillary, is deoxygenated blood. Okay, these are the red blood cells within the deoxygenated blood, and here's the blood plasma. Okay, let's ask ourselves, first of all, what's the partial pressure of oxygen within the blood plasma of deoxygenated blood that's traveling past this alveolus? Well, the partial pressure of oxygen within the blood plasma of this deoxygenated blood traveling through the pulmonary capillary past the alveolus in this example is 40 millimeters of mercury. That's right here. Okay, 40 millimeters of mercury. That means the partial pressure of oxygen within the intracellular fluid of the red blood cells is also 40. Okay, now let's look at the hemoglobin dissociation curve. We can go up, and what do we see? We see that hemoglobin is approximately 75% saturated with oxygen when the partial pressure of oxygen within the blood plasma and thus the intracellular fluid of the red blood cells is 40 millimeters of mercury. This is what the oxygen-hemoglobin dissociation curve shows us. It shows us how saturated hemoglobin within red blood cells is with oxygen at different partial pressures of oxygen, right? It shows us, it looks inside of the red blood cells. And it says, inside of the red blood cell, first of all, how saturated is hemoglobin with oxygen inside of the red blood cell? It's between 0 and 100%. And what determines that is ultimately the partial pressure of oxygen within the blood plasma and thus the intracellular fluid of the red blood cell. So what's the partial pressure of oxygen within the blood plasma of deoxygenated blood? It's 40 millimeters of mercury, and thus the partial pressure of oxygen within the red blood cells themselves is 40 millimeters of mercury. That's right here, okay? And then you just go up and you look at where the line intersects. And you say, okay, well, here is the intersection of the line. Let's move across and we can see, oh, when the partial pressure of oxygen within the blood plasma and thus the intracellular fluid of the red blood cell is 40 millimeters of mercury, then hemoglobin within the red blood cells is about 75% saturated with oxygen. So the red blood cells themselves are about 75% saturated with oxygen. They are only at 3/4 of their oxygen carrying capacity. Now, exactly why this is, I'll explain in a little bit. It'll make more sense if we just go through the whole example, and then I'll explain how the partial pressure of oxygen within the blood plasma and intracellular fluid of the red blood cells is causing this to happen. So let's draw that alveolus again, and then let's draw a pulmonary capillary. Okay, what do we know? Deoxygenated blood is initially traveling through the pulmonary capillary. It's coming from the right ventricle. Okay, and that deoxygenated blood, there's two things going on. The partial pressure of oxygen within the blood plasma, and thus the red blood cells, is 40 millimeters of mercury. And since that's the case, we know that the hemoglobin within the red blood cells is about 75% saturated. Okay, so the red blood cells are 75% saturated with oxygen. And now what's going to happen? Well, as the blood travels past this alveolus, what's going to happen? The partial pressure of oxygen within the air in the alveolus in this example is 100. So there's a partial pressure gradient. And what's going to happen is oxygen is going to move from the air in this alveolus into the blood plasma, the watery component of the blood. And what's it going to do? It's going to drive the partial pressure of oxygen within the blood plasma, the watery component, up to 100. But very few oxygen molecules actually have to move from the air in the alveolus into the blood plasma to accomplish this. So what's the point of doing this at all? Well, look at this. If you drive the partial pressure of oxygen within the blood plasma up to 100, which is what we just accomplished here, right? Oxygen moved from the air in this alveolus into the blood plasma, and it drove the partial pressure of oxygen within the blood plasma up to 100. Now, what is that going to do to the partial pressure of oxygen within the intracellular fluid of the red blood cell? Well, the oxygen will just diffuse right into the red blood cell, and it will drive the partial pressure of oxygen within the red blood cell, the intracellular fluid, right up to 100 as well. Without getting into all the intricacies of this, I can just promise you that when you change the partial pressure of oxygen within the blood plasma, you also change the partial pressure of oxygen within the intracellular fluid of the red blood cell. Okay, but big picture, what's this going to do? Well, if we can drive the partial pressure of oxygen within the blood plasma, and thus the intracellular fluid of the red blood cell, up to 100 millimeters of mercury, which is what we just did right here, and what we've been talking about now for a couple hours between these lectures, then what's going to happen to hemoglobin within the red blood cells? Check this out. Right. Look at this. Hemoglobin will become about 100% saturated with oxygen. Now, what is this? What in the world does that actually mean? And this is where I can explain it. Okay? What dictates how saturated hemoglobin is with oxygen is the partial pressure of oxygen within the intracellular fluid, and thus the blood plasma that exists around the hemoglobin proteins. Okay, let's just say this. If you drive the partial pressure of oxygen within the blood plasma, and thus the intracellular fluid of the red blood cell, up to 100, what that does is it causes the hemoglobin proteins to conformationally shift, almost like troponin does. You know, if calcium binds to troponin, troponin conformationally shifts and pushes tropomyosin off of the myosin binding sites on actin. This is the same sort of thing. Obviously, it's not identical, but the concept is similar. If you drive the partial pressure of oxygen within the blood plasma up to 100, which is what happens at the level of the blood traveling past the alveoli. If you drive the partial pressure of oxygen within the blood plasma up to 100, and thus you drive the partial pressure of oxygen within the intracellular fluid of the red blood cells up to 100, that change in the partial pressure of oxygen within the blood plasma and thus the intracellular fluid of the red blood cells actually causes the hemoglobin molecules, the hemoglobin proteins, to conformationally shift. It changes their structure. And they go from only, they go from being 75% saturated to 100% saturated. Basically, it increases their affinity for oxygen. The hemoglobin proteins will begin to bind more oxygen when the partial pressure of oxygen within the fluid around them goes up to 100 millimeters of mercury. A bigger picture. Okay, here is a pulmonary capillary. Here is a red blood cell, and here's the plasma that exists around it. Okay, to start off with, the partial pressure of oxygen within the blood plasma is 40. The partial pressure of oxygen within the red blood cell is 40. Thus, if the partial pressure of oxygen within the blood plasma and the intracellular fluid of the red blood cell is 40, then the hemoglobin proteins within the red blood cell are 75% saturated with oxygen. This red blood cell is only carrying 75% of its oxygen carrying capacity. Okay, now, if we drive the partial pressure of oxygen within the blood plasma up to 100, we will also drive the partial pressure of oxygen within the intracellular fluid of the red blood cell up to 100. And look at this. If we can drive the partial pressure of oxygen within the blood plasma, and thus the intracellular fluid of the red blood cell, up to 100 millimeters of mercury, which is what happens when the blood travels past the alveoli, then what that does is it causes all these little hemoglobin proteins to conformationally shift so that they increase their binding affinity for oxygen. Right? They increase their affinity for oxygen. And the hemoglobin proteins within the red blood cell conformationally shift, and they will all begin to bind close to 100%. They'll all become close to 100% saturated with oxygen, is what I'm trying to say. When you drive the partial pressure of oxygen within the blood plasma and the cytosol, the intracellular fluid of the red blood cell, up to 100 millimeters of mercury, that increase in the partial pressure of oxygen within the fluid, the plasma and the intracellular fluid of the red blood cell, it has a direct effect on the hemoglobin proteins in the red blood cell itself. And those hemoglobin proteins, they change their orientation and they increase their affinity for binding oxygen. And they all more or less become 100% saturated with oxygen. Now, what does this mean in practical terms, and what's the point of this? So the point is this, okay? Here we will finish this off, okay? Here's the blood, okay? This is deoxygenated blood traveling past the alveoli, in this example, one alveolus here. Okay? This deoxygenated blood within the blood plasma and within the intracellular fluid of the red blood cell, the partial pressure of oxygen is 40. And thus, the 250 million hemoglobin proteins within all these different red blood cells are about 75% saturated with oxygen. All right, and then what happens? Well, there's a partial pressure gradient between the air in the alveoli and the blood plasma within the pulmonary capillary. So because of this partial pressure gradient, oxygen moves from the air in the alveoli into the blood plasma. What does that do? Well, it drives the partial pressure of oxygen within the blood plasma up to 100, and it also drives the partial pressure of oxygen within the intracellular fluid of the red blood cell up to 100. But yet again, very, very little oxygen has actually moved from the air in the alveoli into the blood plasma, right? Because you don't need hardly any oxygen molecules to actually move into water to drive the partial pressure of oxygen of water. And when I say water, right now, I mean the blood plasma, because it's mostly made up of water. You don't need very many oxygen molecules to come into the water to drive the partial pressure of oxygen within the water up to 100 millimeters of mercury. So to this point, it would actually seem like you've accomplished pretty much nothing. And you have in terms of transporting oxygen, but you've done something that's incredibly important. And that is, by driving the partial pressure of oxygen within the blood plasma, and thus the intracellular fluid of the red blood cell up to 100, What that does is it causes all of the 250 million hemoglobin proteins within every red blood cell to conformationally shift and increase their binding affinity for oxygen. They go from being around, 75% saturated, right? Thinking of the oxygen-hemoglobin dissociation curve. When the partial pressure of oxygen within the blood plasma and intracellular fluid of the red blood cell was 40, right? The hemoglobin proteins inside of the red blood cell were 75% saturated. And if we can drive the partial pressure of oxygen within the blood plasma, and thus the intracellular fluid of the red blood cells, up to 100 millimeters of mercury, then all of the hemoglobin proteins within all of these different red blood cells within the blood that's traveling past the alveoli, all these hemoglobin proteins will conformationally shift and increase their affinity for oxygen, and they will all then bind oxygen at 100%. Right? They'll all become 100% saturated with oxygen. Now, why is this important? Well, because so little oxygen up to this point has actually come into the bloodstream, right? Very, very little oxygen molecules actually came into the blood plasma and the intracellular fluid of the red blood cells to drive the partial pressure of oxygen within the within the blood plasma and the red blood cells up to 100 millimeters of mercury. Very little oxygen has actually come into the blood up to this point. So what's the point? Well, it's to cause the hemoglobin molecules, the hemoglobin proteins, to conformationally shift and bind more oxygen, because that's how our blood actually transports oxygen, right? In our bloodstream, we transport oxygen bound to hemoglobin within our red blood cells. We can hardly carry any oxygen within the watery component of our blood, because the watery component of our blood is mostly made up of water, and thus it's polar. Oxygen is nonpolar. It can't exist very well with the watery component of our blood. We can't transport much oxygen in our blood plasma. But what we can do, and what we clearly have evolved to do, is to resolve that problem by having red blood cells, which inside have hemoglobin. And the hemoglobin within the red blood cells can latch on to oxygen and transport the oxygen that way. And that's how we transport the vast majority of oxygen through our bloodstream. It's bound to hemoglobin within our red blood cells. Think about this. Again, 25 trillion red blood cells in the human body. Each red blood cell has 250 million hemoglobin proteins inside, each capable of binding 4 oxygen molecules. Basically, all the oxygen within your bloodstream is carried within your red blood cells, not in your blood plasma. The purpose of driving the partial pressure of oxygen within the blood plasma up to 100 millimeters of mercury, and thus the intracellular fluid of the red blood cell, which is also water, right, up to 100 millimeters of mercury, is to actually influence the hemoglobin proteins within the red blood cells. And that increase in the partial pressure of oxygen within the blood plasma and the intracellular fluid of the red blood cells tells the hemoglobin proteins, essentially, you need to go from binding 75% oxygen, being 75% saturated, to 100% saturated. It causes a conformational shift within the hemoglobin proteins, and they begin to bind more oxygen. And this is how the, vast majority of oxygen is actually going to be taken from the alveoli into the bloodstream. It's mostly going to be bound to hemoglobin, because very little oxygen can actually exist within the blood plasma, the watery component, but enormous amounts of oxygen can be carried by red blood cells bound to hemoglobin. Again, think about it. Very little oxygen is actually coming into the blood plasma, into the watery component of the blood. But each one of these red blood cells that's going past this alveolus in this example, each one of these red blood cells has 250 million hemoglobin proteins within it, each capable of binding 4 oxygen molecules. And what we're doing is, as the red blood cell travels past this alveolus, it goes from binding 75% oxygen to binding 100% oxygen. It goes from being 75% saturated to 100% saturated. The red blood cells themselves increase their oxygen carrying capacity as they move past the alveoli by 25%. And that's where all of the oxygen is going to be extracted from the air in the alveoli. When it's extracted, it's pulled into the bloodstream, and it actually all ends up being bound to hemoglobin within the red blood cells. It's not carried in the blood plasma. So let me explain that just a little bit more. So something that really confuses people for good reason is what I have been telling you is that if the partial pressure of oxygen within the blood plasma and the partial pressure of oxygen within the intracellular fluid of the red blood cell is 100 millimeters of mercury, then there's not actually very much oxygen that exists within the blood plasma and the intracellular fluid. Okay. I think I've spent a lot of time trying to make that point. But then at the same time, what I tell you should seem rather contradictory, which is you have this red blood cell. Inside of this red blood cell, there's 250 million hemoglobin molecules. To start off with, this red blood cell, the hemoglobin within it, is 75% saturated with oxygen. That means the 250 million hemoglobin molecules within this one red blood cell each have 3 oxygen molecules bound to them, and they could have 4. They're 75% saturated. And then the red blood cell, as it travels past this alveolus, the red blood cell then, it goes to having its hemoglobin 100% saturated. It's more like 98%, but close to 100% saturated with oxygen. So the reason that I'm saying this should seem contradictory is because think about how many oxygen molecules you would need in order to do this. To allow for a red blood cell, the hemoglobin within a red blood cell, to go from 75% saturation to 100% saturation, how many oxygen molecules would the red blood cell have to gain? It would have to gain 250 million oxygen molecules in order for that to happen, because again, to go from 75 to 100% saturated, that means essentially that all 250 million hemoglobin molecules within the red blood cell would have to gain an oxygen molecule so that they all had 4 oxygen molecules bound to them. That's how you would go from 75 to 100% saturation, so that all the 250 million hemoglobin molecules within the red blood cell have 4 oxygen molecules bound to them. That's 100% saturation. But again, that should seem really problematic because I've told you so many times that there's not very much oxygen that actually exists within the blood plasma and the intracellular fluid when the partial pressure of oxygen within the blood plasma and the intracellular fluid is 100. If there's not very much oxygen within the blood plasma and the intracellular fluid, then how are these red blood cells gaining each, and there's trillions of red blood cells in the body, how are each of these red blood cells, as they go past an alveolus, each of them gaining 250 million hemoglobin molecules, 250 million oxygen molecules? How are each, let's make sure that I don't confuse you, how are each of these red blood cells gaining 250 million oxygen molecules as they go past an alveolus to go from 75% saturated to 100% saturated, meaning the hemoglobin goes from 75 to 100% saturation? How could that be possible if there's so little oxygen within the blood plasma and the intracellular fluid of the red blood cell? The answer is there's a little bit of a loop that's going to go on here, but it happens at such an incredibly fast speed that oftentimes when we discuss this, we think about these partial pressures as staying static. I'll explain what all that means in a minute. So we've got, first of all, we've got oxygen within the air and the alveoli, right? The partial pressure of oxygen within the air and the alveoli is 100. The partial pressure of oxygen within the blood plasma and intracellular fluid of the red blood cell is 40. You've seen this a million times. You know what happens. Oxygen is going to move from the air in this alveolus into the blood plasma. That's going to drive the partial pressure of oxygen within the blood plasma up to 100. Then the oxygen is going to move from the blood plasma into the intracellular fluid of the red blood cell. Over a very short period of time, the partial pressure of oxygen within the red blood cell, intracellular fluid of the red blood cell, would rise, theoretically, to 100. The partial pressure of oxygen within the blood plasma, as it's moving from the plasma into the intracellular fluid of the red blood cell, might fall a little bit, but then oxygen is just going to come. It's going to have a diffusion gradient again, and it's just going to rip right back from the air in the alveoli into the blood plasma and drive the partial pressure of oxygen within the blood plasma up to 100. So ultimately what you're going to get is this. The partial pressure of oxygen within the air in the alveoli will be 100. The partial pressure of oxygen within the blood plasma will be 100. And the partial pressure of oxygen within the intracellular fluid of the red blood cell will be 100. Importantly, that's going to cause a conformational shift of the hemoglobin proteins that exist within this red blood cell that we're looking at here. And then what's going to happen? These hemoglobin proteins, what are they going to do? They're going to start binding more oxygen. These hemoglobin molecules are going to have a higher affinity for oxygen. So the hemoglobin molecules within this red blood cell are going to start binding more oxygen. But where do they get the oxygen from? Where do you think the oxygen is coming from? Well, it's coming from the intracellular fluid of the red blood cell. When I say that hemoglobin within a red blood cell binds more oxygen, the place that it's extracting that oxygen from is from the intracellular fluid of the red blood cell that the hemoglobin protein exists within. So these hemoglobin proteins, when they're binding oxygen, they're taking the oxygen from the intracellular fluid of the red blood cell. And what does that mean? Well, by the time that, let's erase this a little bit, but by the time that oxygen has moved from the intracellular fluid of the red blood cell to being bound to hemoglobin, oxygen is no longer within the intracellular fluid of the red blood cell. It's bound to hemoglobin. Right? So, I mean, if oxygen was within the intracellular fluid of the red blood cell, but then it goes and it binds one of the oxygen molecules within the intracellular fluid of the red blood cell, it goes and it binds to a hemoglobin molecule. Now it's bound to a hemoglobin molecule. It's not within the intracellular fluid of the red blood cell anymore. So what effect is that going to have on the partial pressure of oxygen within the red blood cell, within the intracellular fluid of the red blood cell? What I'm saying is, as hemoglobin within this red blood cell binds more and more oxygen, it's extracting that oxygen from the intracellular fluid of this red blood cell. So what's going to happen to the partial pressure of oxygen within the intracellular fluid of this red blood cell if the oxygen is being extracted from the intracellular fluid by being bound to hemoglobin? The answer is the partial pressure of oxygen within the red blood cell will fall. The partial pressure of oxygen within the intracellular fluid of the red blood cell will fall as more and more of the oxygen within the intracellular fluid of the red blood cell becomes bound to hemoglobin. I'm not going to attribute numbers to this because I don't think it's helpful, and it results in an endless conversation that has no meaningful purpose. By that I mean I'm not going to say that the partial pressure of oxygen within the intracellular fluid falls to 70 or something. It makes no sense to do that. All you have to realize is that if oxygen within the intracellular fluid of the red blood cell is leaving the intracellular fluid of the red blood cell to be bound to hemoglobin within that red blood cell, then the partial pressure of oxygen within the intracellular fluid of the red blood cell is going to decrease. It has to, because there's less oxygen within the intracellular fluid of the red blood cell. And then what do you have again? Well, you have a gradient. Oxygen now can move from the blood plasma again into the intracellular fluid of the red blood cell. And that's going to drive the partial pressure of oxygen within the red blood cell up again, right? But importantly, that's also going to drive the partial pressure of oxygen within the plasma down as it moves from the plasma into the intracellular fluid of the red blood cell. And that's going to create a gradient between the partial pressure of oxygen within the air in the alveoli and the partial pressure of oxygen within the blood plasma. So now oxygen will move from the air in the alveoli into the blood plasma again. So this loop here is just going to keep happening again and again and again and again. I mean, like at an incredibly rapid pace. We're talking milliseconds here, how quickly this is actually going to happen. The point is, the red blood cells are getting a continual supply of oxygen that's actually coming from the air in the alveolus. This is how we can explain how a red blood cell is actually capable of gaining 250 million oxygen molecules when it becomes 100% saturated as it travels past the alveolus. And that's how we can explain this while simultaneously saying that there's not very much oxygen that actually exists within the blood plasma or the intracellular fluid. That's how we can explain how a red blood cell can actually gain an enormous amount of oxygen as it travels past the lungs, past this alveolus. Because, yet again, one more time, if the partial pressure of oxygen within the intracellular fluid of the red blood cell is 100, we know that that causes a conformational shift of the hemoglobin molecules within this red blood cell, and then they're going to start binding more oxygen. Where do they get that oxygen from? Well, of course, they get it from the intracellular fluid of the red blood cell that they're within. And as the hemoglobin binds more and more oxygen and extracts it from the intracellular fluid of the red blood cell, then the partial pressure of oxygen within the intracellular fluid of the red blood cell will fall. Right? And that then will allow for more oxygen to travel from the blood plasma into the intracellular fluid, because the partial pressure of oxygen within the blood plasma would be 100, and the partial pressure of oxygen within the intracellular fluid of the red blood cell would be less. And as the oxygen moves from the blood plasma into the intracellular fluid of the red blood cell, that means the partial pressure of oxygen within the blood plasma will fall. And that will allow for more oxygen to come from the air in the alveolus into the blood plasma. It creates a gradient. The partial pressure of oxygen within the air within the alveolus would be greater than the partial pressure of oxygen within the blood plasma. So now more oxygen can come from the air in the alveolus into the blood plasma, and as more and more oxygen is extracted from the intracellular fluid of the red blood cell by being bound to hemoglobin within the red blood cell, that will continuously drive down the partial pressure of oxygen within the intracellular fluid of the red blood cell so that oxygen can keep coming into the red blood cell from the blood plasma. And this just keeps happening until all of the 250 million hemoglobin molecules within this red blood cell gain one oxygen molecule, right? So they can become 100% saturated. So this red blood cell can gain 250 million hemoglobin molecules. The vast majority of those 250, I keep saying that on accident, this red blood cell is going to gain 250 million oxygen molecules. The vast majority of those 250 million oxygen molecules that this red blood cell gains is actually coming from the air in the alveoli. That oxygen, though, has to first get from the from the air in the alveoli into the plasma, and then into the intracellular fluid, and then it binds to the hemoglobin molecules within the red blood cells. For those of you that maybe had that question, which was, how can a red blood cell, one red blood cell, gain so much oxygen, 250 million oxygen molecules, when there's so little oxygen within the blood plasma and within the intracellular fluid of the red blood cell? How could a red blood cell gain so much oxygen when there's so little oxygen within the plasma and the intracellular fluid? I hope that this answered that question. It can gain so much oxygen because oxygen just keeps coming in from the air within the alveoli, entering into the plasma and then entering into the red blood cell and then binding to the hemoglobin within the red blood cell. The oxygen just keeps following a gradient from the air in the alveoli into the plasma, into the intracellular fluid, and then binding to hemoglobin within the red blood cell. So the vast, vast, vast majority of oxygen carried by our bloodstream, right, is of course bound to hemoglobin within our red blood cells and not existing within the plasma or the intracellular fluid of the red blood cells. And when red blood cells become oxygenated at the level of the lungs as they travel past the alveoli, they're getting all of that oxygen from the air within the alveoli. The oxygen just kind of has to follow a bit of a loop to continuously leave the air into the plasma and go into the intracellular fluid of the red blood cell. And that just keeps happening and happening and happening. And this happens in phenomenally fast, by the way. Within milliseconds, these red blood cells become 100% saturated with oxygen, the hemoglobin within them. But that process just keeps happening, oxygen moving from the air into the plasma, into the intracellular fluid of the red blood cell, binding to hemoglobin, until all of the hemoglobin within a red blood cell are essentially 100% saturated with oxygen. So it absolutely remains true that there's not very much oxygen that exists within blood plasma or within the intracellular fluid of red blood cells. It is essential that you drive the partial pressure of oxygen within the plasma and the intracellular fluid of the red blood cell up so that hemoglobin will become more saturated with oxygen. That's the true value of having more oxygen within the plasma and the intracellular fluid. It's influencing hemoglobin. But the place where hemoglobin is actually gaining all of this oxygen from, as it travels past the alveoli, is actually from the air in the alveoli. So I hope that that was helpful in explaining how there can be very little oxygen within the plasma and intracellular fluid, but yet a red blood cell can gain so much oxygen as it travels past our lungs. Just so that we're clear with terminology, what you've seen throughout all of this is blood getting oxygenated. You've seen what's called deoxygenated blood travel past the lungs, meaning past the alveoli, and become what's known as oxygenated blood. Now that also involves the exchange of carbon dioxide, which is coming, but you've seen half of the oxygenation process. So if you think about it and you say, well, blood has become oxygenated, just think about the name. It means that the blood has gained a bunch of oxygen, which is clearly what has happened here. Right? A bunch of oxygen has moved from the air in the alveoli into the blood, particularly into hemoglobin within the red blood cells. So the blood has become oxygenated as it goes past the lungs. Now, what does oxygenated blood actually look like? Okay, so if you look at oxygenated blood, just to look at it structurally, first of all, the partial pressure of oxygen within the air in the alveoli is still going to be pretty much 100 millimeters of mercury. And that should tell you how much oxygen there actually is within the air that we breathe. Because despite the fact that literally billions of oxygen molecules will have left the air in the alveoli and gone into the bloodstream, that's still not enough to meaningfully bring down the partial pressure of oxygen within the air in the alveoli. So again, once the blood has gotten past the alveoli, it actually doesn't have to get completely past it, but let's say 3/4 of the way past an alveolus, like in this example, what you're going to see is that the partial pressure of oxygen within the air in the alveoli would still be 100. The partial pressure of oxygen within the blood plasma would be 100. The partial pressure of oxygen within the intracellular fluid of the red blood cell would be 100. And the hemoglobin within the red blood cells of oxygenated blood would be 100% saturated, approximately, very close to 100% saturated with oxygen. So the reason that you would end up with 100, 100, 100 is because oxygen would keep coming, as you know, from the air into the blood plasma, into the intracellular fluid of the red blood cell, and then binding to hemoglobin within the red blood cell. And that process would keep happening and happening and happening, and it actually is completed over the course of milliseconds. But that process would keep happening until all the hemoglobin within the red blood cell was 100% saturated with oxygen. And at that point, of course, the partial pressure of oxygen within the intracellular fluid of the red blood cell would be stuck at 100, because the partial pressure of oxygen within the blood plasma would be stuck at 100, ultimately all because the partial pressure of oxygen within the air in the alveoli is 100. As long as the partial pressure of oxygen within the air in the alveoli is 100, then that is the most that the partial pressure of oxygen within the blood plasma and the intracellular fluid of the red blood cell can be. Think about it. The only way that you could get the partial pressure of oxygen within the blood plasma or the intracellular fluid of the red blood cell to be higher would be to drive up the partial pressure of oxygen within the air in the alveoli. That'd be the only way to do it. And the partial pressure of oxygen within the air in the alveoli is 100. So thus the partial pressure of oxygen within the intracellular fluid of the red blood cell and blood plasma can't be any higher than 100 either. Once hemoglobin is 100% saturated with oxygen within the red blood cells, everything equilibrates at 100 millimeters of mercury with regard to the partial pressure of oxygen in the intracellular fluid, in the plasma, and of course that doesn't change, but in the air in the alveoli. So this is what oxygenated blood looks like. And let's remind ourselves anatomically of where the deoxygenated blood was coming from and where the oxygenated blood is now going. So this image is showing deoxygenated blood being pumped out of the right ventricle into the pulmonary arteries. And then the blood travels, this deoxygenated blood travels through the pulmonary arteries into pulmonary arterioles and then pulmonary capillaries. Then the blood becomes oxygenated at the lungs, which we just spoke about. And now this oxygenated blood is going to travel through the pulmonary veins back to the left atrium, left ventricle, and then be pumped out into the aorta, which is also the beginning of the systemic circuit. That whole oxygenation process of blood happened within the pulmonary circuit. Right? I don't think we need to go back over the circuits, but just to be clear. Okay? So now we have this oxygenated blood that's been pumped from the left ventricle out into the systemic circuit. These systemic arteries are going to do what? They're going to deliver oxygenated blood to the tissues of our body. Okay? These could be muscle cells, right? This could be muscle tissue, skeletal muscle tissue. These could be arteries taking blood to skeletal muscle tissue during exercise, for example. And the question becomes, well, what happens as this oxygenated blood travels past the tissues of our body? Clearly, we know that we want the oxygen that's within the blood that we just got from the air in the alveoli. We want the oxygen that's within the blood to go into the tissues so the tissues can use the oxygen to make ATP through oxidative phosphorylation. But how does that process actually play out? So what this image is showing you is it's showing you oxygenated blood traveling through what would be an arteriole. Okay, that's a small artery. Okay. The oxygenated blood is traveling through an arteriole, and then it moves into a capillary bed, which is surrounding, in our example, muscle cells. Okay, those are muscle cells. It's muscle tissue. Okay, so here's this oxygenated blood traveling through an arterial. You'll notice that the partial pressure of oxygen within the blood plasma of the oxygenated blood is 95 millimeters of mercury. If you read enough textbooks and talk to enough scientists and read enough studies, you'll find out that the value just differs a little bit from one person to the next in what they think about the partial pressure of oxygen within the blood plasma of oxygenated blood. It's always somewhere around 100. I took this image from another textbook that I like, which is why it differs a little bit from what's in your textbook. But at the end of the day, the principles are exactly the same and the numbers are right around the same. Okay, so don't be confused by that. This is oxygenated. This is oxygenated blood traveling through in arterial into a capillary bed, and the capillary bed surrounds muscle cells. Those could actually be neurons or any other type of cell, but we're going to call them muscle cells because we've talked about those a lot in this class. So what's going to happen to this oxygenated blood once it enters initially into the capillary? This is a systemic capillary. And the capillary, again, it would be a bed of capillaries, but this capillary exists around muscle cells. So let's try to draw that. So let's pretend that this right here is a capillary within the systemic circuit. Right? It's taking oxygenated blood past muscle cells. Okay, so let's remind ourselves about what oxygenated blood looks like. Oxygenated blood within the blood plasma, the partial pressure of oxygen within the blood plasma is 100. The partial pressure of oxygen within the intracellular fluid of the red blood cells is 100. Hemoglobin within the red blood cells is approximately 100% saturated with oxygen. So that is what oxygenated blood looks like. And this oxygenated blood right now is traveling through a capillary past these muscle cells. Okay, so right outside of the muscle cells is the interstitial fluid, the fluid that exists right outside of cells. And in that interstitial fluid, the partial pressure of oxygen nearest or most near the capillary would be about 40 millimeters of mercury. And that would be all over the place. Actually down here, the partial pressure of oxygen would be lower and lower as you get towards the cells. So I'll talk about that in just a second. Okay, so the partial pressure of oxygen within the interstitial fluid, right? Because that's water, right? And in that fluid, there's some oxygen. The partial pressure of oxygen within that interstitial fluid that's right next to the capillary would be approximately 40 millimeters of mercury. And something that's very important is the oxygen that's within the interstitial fluid is constantly being dragged towards the muscle cells, specifically towards the mitochondria, which are inside of the muscle cells. As you get closer and closer to the mitochondria, the partial pressure of oxygen gets lower and lower and lower and lower. Right outside of the mitochondria, the partial pressure of oxygen, some people estimate, is about 2 millimeters of mercury. So as we get closer and closer to the cell, the partial pressure of oxygen is less. Inside of the cell, it's less. And as we approach the mitochondria, the partial pressure of oxygen gets less and less and less. What this means is there's a constant gradient, partial pressure gradient, that's pulling oxygen from the interstitial fluid into the muscle cell and into the mitochondria. So you have to recognize that for the next thing that is coming. The oxygen within the interstitial fluid is constantly being pulled towards and into the muscle cells and into the mitochondria of the cells that are around, of course, the interstitial fluid, the muscle cells. So what's actually going to happen? Oxygenated blood is going to enter into the capillary. We know the partial pressure of oxygen within the interstitial fluid outside of the capillary is 40 millimeters of mercury. we know that the partial pressure of oxygen within the blood plasma of oxygenated blood is 100 millimeters of mercury. We know inside of the red blood cell, the partial pressure of oxygen within the intracellular fluid inside of the red blood cell is 100, and we know that hemoglobin is approximately 100% saturated with oxygen. Okay, so we have a partial pressure gradient here. The partial pressure of oxygen within the blood plasma is 100. The partial pressure of oxygen within the interstitial fluid outside of the muscle cells is 40. So what's going to happen is oxygen is going to begin to move from the blood plasma into the interstitial fluid. Now this is an exchange of gases between two fluids. So what you would think would happen is the partial pressure of oxygen within the blood plasma would fall, which it does, and you would think that the partial pressure of oxygen within the interstitial fluid would rise, which it would perhaps a little bit. But the issue is, as soon as any oxygen moves into the interstitial fluid, it immediately is getting dragged right towards the cell and into the cell, into the muscle cell, and into the mitochondria. So more or less what you have to pretend is that the partial pressure of oxygen within the interstitial fluid more or less stays static at 40. Okay? Yes, oxygen is moving from the blood plasma into the interstitial fluid, and that would cause the partial pressure of oxygen to rise within the interstitial fluid in a very transient manner. But incredibly quickly, we're talking, again, incomprehensible speeds, that oxygen would just immediately be being pulled towards and into the cells around the interstitial fluid. It would just follow its partial pressure gradient into the cells and go right into the mitochondria. So just for the sake of simplifying things slightly, you can pretend that the partial pressure of oxygen within the interstitial fluid stays more or less static at 40 millimeters of mercury. So what would happen then? Well, oxygen would move from the blood plasma into the interstitial fluid. Right? And the partial pressure of oxygen within the blood plasma would begin to fall. It would begin to fall until it approached 40. At the same time, oxygen would be leaving the intracellular fluid of the red blood cell out into the plasma. And that would transiently, of course, cause the partial pressure of oxygen within the plasma to rise, but then it would get pulled right into the interstitial fluid again. Okay, so this is like the same loop that we looked at before, but in the opposite direction. Okay. Again, what's happening? The partial pressure of oxygen within the blood plasma of oxygenated blood is 100. The partial pressure of oxygen within the interstitial fluid outside of capillaries is 40. So there's a gradient here. Oxygen is going to move. Let's not attribute numbers to this. Let's just show the path, and then you can use your imagination a little bit from there. So as oxygen moves from the blood plasma into the interstitial fluid, the partial pressure of oxygen within the blood plasma will fall. That creates a gradient between the partial pressure of oxygen within the intracellular fluid of the red blood cell and the partial pressure of oxygen within the blood plasma. So then the oxygen within the intracellular fluid of the red blood cell is going to leave out into the plasma. That would cause a minor rise in the partial pressure of oxygen within the blood plasma, which would then continuously pull the oxygen from the blood plasma into the interstitial fluid. And this loop of oxygen moving from the plasma into the interstitial fluid, and then oxygen moving from the intracellular fluid of the red blood cell into the plasma, and then into the interstitial fluid. It's just going to keep happening and happening and happening until we hit an equilibrium. And that equilibrium is going to be 40 millimeters of mercury. Eventually, the partial pressure of oxygen within the blood plasma will become 40 millimeters of mercury. The partial pressure of oxygen within the intracellular fluid of the red blood cell will become 40. They will equilibrate with the interstitial fluid. Everything will become 40. By that I mean the partial pressure of oxygen within the intracellular fluid within the blood plasma and within the intracellular fluid of the red blood cell will, over time, as more and more oxygen moves into the interstitial fluid, more and more and more, and this is happening as the blood moves along the length of the capillary as well. As more and more oxygen goes into the interstitial fluid from the blood collectively, eventually they're all going to get stuck at 40 millimeters of mercury, because that's what the interstitial fluid is, and you can't go any lower than that. To go lower than 40 millimeters of mercury, you would need the partial pressure of oxygen within the interstitial fluid to be lower than 40, and it's not. So everything is going to get stuck at a partial pressure of oxygen of 40 millimeters of mercury. So what is the actual point of doing this? Because what have we actually accomplished? If now we have blood within the systemic capillary, and the partial pressure of oxygen within the blood plasma is 40. The partial pressure of oxygen within the intracellular fluid of the red blood cell is 40, and the partial pressure of oxygen within the interstitial fluid is 40. What have we actually accomplished? To this point, very, very little oxygen has actually entered into the interstitial fluid. Where has all of this oxygen come from that's gone into the interstitial fluid from the blood? It's all come from either the blood plasma or the interstitial fluid of the red blood cell, which again is just essentially the same thing. It's all oxygen that exists within fluid inside of the blood plasma and the intracellular fluid. And there's not very much oxygen that exists within fluid within water. So to drive the partial pressure of oxygen within the blood plasma and the intracellular fluid of the red blood cells down to 40 millimeters of mercury doesn't actually take much. Very few oxygen molecules would actually have to leave the blood plasma and the intracellular fluid of the red blood cell in order for them both to be at 40 millimeters of mercury. So we've really given hardly any oxygen to the cells of the body, to these muscle cells. So there must be a reason beyond delivering oxygen that we want to drive down delivering oxygen from the blood plasma and intracellular fluid. There must be a reason beyond that why we want to drive down the partial pressure of oxygen within the blood plasma and thus the intracellular fluid to 40 millimeters of mercury. So let's talk about that. To be able to thoroughly answer that question, we need to look back at the oxygen-hemoglobin dissociation curve. So, what does oxygenated blood look like? The partial pressure of oxygen within the blood plasma and intracellular fluid of the red blood cell is 100. And thus hemoglobin within the red blood cell is very close to 100% saturated with oxygen. What happens as this oxygenated blood goes past the muscle cells? Well, we know that the partial pressure of oxygen within the interstitial fluid around the muscle cells, close to the capillary, is 40 millimeters of mercury. What that ultimately did is what? It drove down the partial pressure of oxygen within the blood plasma and within the intracellular fluid of the red blood cell to 40. So all of these locations are at equilibrium. The partial pressure of oxygen within the interstitial fluid is 40. The partial pressure of oxygen within the blood plasma is 40. The partial pressure of oxygen within the intracellular fluid is 40. And I, of course, made the point that very little oxygen would actually have to leave the blood plasma and the intracellular fluid of the red blood cell in order for this to happen, because there's not very much oxygen within the watery component of our blood, the plasma and intracellular fluid. It's all within the red blood cells. So what we've done here, importantly, is we really haven't given very much oxygen to the interstitial fluid, but what we have done is we've driven the partial pressure of oxygen within the plasma and intracellular fluid of the red blood cell down to 40 millimeters of mercury. And what has that done to the oxygen-hemoglobin dissociation curve? Take a look. When the partial pressure of oxygen within the plasma, particularly the intracellular fluid, is driven down to 40 millimeters of mercury, what happens to hemoglobin? Hemoglobin goes from being 100% saturated when the partial pressure of oxygen within the intracellular fluid is 100 to being about 75% saturated with oxygen when we drive the partial pressure of oxygen within the intracellular fluid down to 40 millimeters of mercury. Another way of saying this is, if you drive the partial pressure of oxygen within the intracellular fluid of the red blood cell down, hemoglobin will unload 25% of its oxygen. Another way of thinking about that is, hemoglobin's now going to be 75% saturated, which means that if there's 250 million hemoglobin proteins within a red blood cell, and they're all 100% saturated, they all have 4 oxygen molecules bound to them, and now they all become 75% saturated, that means each of the 250 million hemoglobin molecules within the red blood cell will release 1 oxygen molecule. So collectively, if the red blood cell, the hemoglobin within it, goes from being 100% to 75% saturated with oxygen, the red blood cell will release 250 million oxygen molecules. And that's where all of the oxygen is going to come from that actually goes into the interstitial fluid and into the muscle cells. And not literally all, but like the vast 90+% majority of oxygen is actually going to be going into the interstitial fluid and into the muscle cells. That oxygen is actually coming from the red blood cells bound to hemoglobin. Let me make my point one more time if I'm not being clear enough here. The purpose of driving the partial pressure of oxygen within the blood plasma and within the intracellular fluid of the red blood cell down to 40 millimeters of mercury is to influence hemoglobin within the red blood cells. Because if you can drive the partial pressure of oxygen within the intracellular fluid of the red blood cell down to 40, which we've done now, then that will cause a conformational shift within the hemoglobin molecules, proteins, within the red blood cell. And that shift allows them to release 25% of their oxygen. And that, compared to the amount of oxygen within the intracellular fluid and blood plasma, is an enormous amount of oxygen comparatively to the oxygen that's being carried actually in the fluid, blood, or water of the blood. So you would maybe ask, well, how would that oxygen actually get from the red blood cell into the interstitial fluid and then into the muscle cells? Well, the answer is, well, hemoglobin would release that oxygen. And where would the oxygen go? If hemoglobin releases the oxygen, hemoglobin is actually releasing that oxygen into the intracellular fluid of the red blood cell. And that, again, we're not going to play a numbers game here because it makes no sense and it's way more confusing than it needs to be. If hemoglobin releases that oxygen into the intracellular fluid of the red blood cell, then the partial pressure of oxygen within the intracellular fluid of the red blood cell will rise. Because the oxygen is no longer bound to hemoglobin, it's actually in the fluid, the cytosol intracellular fluid of the red blood cell. So the partial pressure of oxygen within the intracellular fluid of the red blood cell will rise, and it will be greater than the partial pressure of oxygen within the blood plasma. And then where will the oxygen go? It'll go from the intracellular fluid of the red blood cell into the blood plasma, which will drive up the partial pressure of oxygen within the blood plasma so that it's higher than the interstitial fluid, and then the oxygen will travel from the blood plasma into the interstitial fluid, where it can then follow its gradient down into the muscle cell and into the mitochondria. So to summarize, the purpose of bringing oxygenated blood into systemic capillary beds is to supply the cells, in our example, the muscle cells, that lie next to the capillary beds with oxygen. Okay? Clear, I think it's somewhat clear that really the point of the systemic circuit is to deliver oxygen to the cells of our body. And I'm trying to show you how that happens. Oxygenated blood is going to go through a systemic capillary, and it's going to then deliver oxygen to the cells of the body. The question is, how does it do that? And that is obviously a lot more complicated. To summarize how that's accomplished, first of all, oxygenated blood has a partial pressure of oxygen within its blood plasma of 100, a partial pressure of oxygen within the intracellular fluid of the red blood cells of 100, and hemoglobin is, as we know, 100%, close to 100% saturated with oxygen. That's oxygenated blood. Then, as the blood travels through the capillary bed, what will happen is oxygen within the blood will follow its partial pressure gradient. The partial pressure of oxygen within the blood plasma is 100. The partial pressure of oxygen within the interstitial fluid near the muscle cells and right outside of the capillary is 40 millimeters of mercury. So oxygen is going to follow its diffusion gradient and is going to move from the blood plasma into the interstitial fluid until the partial pressure of oxygen, in my example, is 40 in the blood plasma and 40 in the intracellular fluid of the red blood cell. So everything is 40. Very little oxygen has actually gone into the blood plasma. Has actually gone into the interstitial fluid at this point. Very little oxygen has actually left the blood and gone into the interstitial fluid and traveled into the cells, the muscle cells, at this point. So what was the point of doing all of this? To drive the partial pressure of oxygen within the red blood cell down to 40 millimeters of mercury so that it will influence hemoglobin. It will influence, if you look at the oxygen-hemoglobin dissociation curve, driving the partial pressure of oxygen within the intracellular fluid of the red blood cell down to 40 millimeters of mercury causes a conformational shift of the hemoglobin proteins within the red blood cells. That causes them to go from being 100% saturated to 75% saturated with oxygen, meaning it causes them to release 25% of their oxygen, right? One oxygen molecule, each of the 250 million hemoglobin proteins will release in a red blood cell. That translates into 250 million oxygen molecules being released by a red blood cell if you can drive the partial pressure of oxygen down to 40 millimeters of mercury within the intracellular fluid of it. Where does that oxygen go? It goes from being bound to hemoglobin into the intracellular fluid of the red blood cell, driving the partial pressure of oxygen within the intracellular fluid of the red blood cell up so that it is higher than the partial pressure of oxygen within the blood plasma. It will follow its gradient and move from the intracellular fluid into the blood plasma and drive the partial pressure of oxygen within the blood plasma up so that it is greater than the partial pressure of oxygen within the interstitial fluid outside of the capillary, and then the oxygen will move from the blood plasma into the interstitial fluid and down into the muscle cell. And this loop will continue happening over and over. I mean, not over and over and over again, but the loop will continue until what? When will this end? When will this finally be over? Well, it'll be over by the time that you have created what's known as deoxygenated blood. By the time that this blood has gone past this systemic capillary, what is it actually going to look like? Well, there's going to come a point when hemoglobin reaches 75% saturation. Hemoglobin is going to release 25% of its oxygen, and all that oxygen is going to travel into the, it's going to travel into the intracellular fluid of the red blood cell, into the blood plasma, and into the interstitial fluid, and it's going to keep following that path. But eventually, hemoglobin is just going to be 75% saturated, and it can't become any less than that, right? At a partial pressure of oxygen of 40 millimeters of mercury in the intracellular fluid, hemoglobin can't become any less saturated than 75 millimeters. I mean, any less saturated than 75%. If you wanted hemoglobin to unload more oxygen, which we'll talk about later on, there's a variety of things that you could do, and one of them would be to drive the partial pressure of oxygen within the intracellular fluid of the red blood cell down even more. That would actually cause hemoglobin to unload more of its oxygen, but that can't happen here because the partial pressure of oxygen within the intracellular fluid, as we know, the lowest it can get in this example is 40, because that's what the partial pressure of oxygen within the interstitial fluid is. It can't get any lower than that. So hemoglobin, all it can do is unload 25% of its oxygen, and that's it. That's a lot of oxygen, but that's all it can do. So then what are you left with? Well, what you're left with is this. The partial pressure of oxygen within the intracellular fluid of the red blood cell would be 40. The partial pressure of oxygen within the blood plasma would be 40. And hemoglobin within the red blood cells would be 75% saturated with oxygen. It will have unloaded 25% of its oxygen, but that's all that it can do. If hemoglobin can't unload any more oxygen, then you can't unload any more oxygen into the intracellular fluid and drive the partial pressure of the intracellular fluid within the red blood cell up anymore. That means no more oxygen can go into the blood plasma and into the intracellular fluid, so you're just stuck at that point. Everything ends up being 40 because that is what the partial pressure of oxygen is within the interstitial fluid. The partial pressure of oxygen within the interstitial fluid will be 40, the partial pressure of oxygen within the plasma will be 40, and the partial pressure of oxygen within the intracellular fluid of the red blood cell will be 40, and the hemoglobin within it will be 75% saturated. This is what deoxygenated blood looks like. You have seen the first half, not including carbon dioxide, of the deoxygenation process, how the blood supplies oxygen to the tissues of our body as it travels through systemic capillaries. I hope most importantly, what you've realized is that the vast majority of oxygen that's actually traveling from our blood into the interstitial fluid and thus into the cells of our body is coming from the red blood cells. It's coming from being bound to hemoglobin. It's not coming from the blood plasma or the interstitial fluid, right? Yes, the oxygen does go into that when it leaves hemoglobin, but really all the oxygen that's carried in our blood and then goes into the interstitial fluid and tissues of our body, that oxygen is coming from being inside of our red blood cells bound to hemoglobin. And the whole purpose of driving the partial pressure of oxygen within the blood plasma and the intracellular fluid of our red blood cells down is to influence hemoglobin within our red blood cells so that it will release more oxygen, because that's really where all the oxygen is coming from that's going to go into our cells. If there was no hemoglobin, there would be very little oxygen that would actually be carried by our blood. There wouldn't be nearly enough oxygen carried in our bloodstream if all we had was the watery component of our blood to supply enough oxygen to our cells in order to be able to survive. I know I've said this, but our red blood cells and the hemoglobin within them is how our bodies get around the fact that atmospheric oxygen is incredibly nonpolar, and our blood, which is made up of water and red blood cells, is very polar. It's made up of water. They don't go together. So how do you get around that? Well, you create hemoglobin within red blood cells to actually be able to transport the oxygen outside of the water. So point being, if you want that oxygen to actually get into the cells of your body, there's got to be a way to influence the blood so that hemoglobin will let go of some of that oxygen that it's holding on to. And that's done through dropping these partial pressures of oxygen within the plasma and intracellular fluid. So here's an image to kind of summarize the deoxygenation process. You know that oxygenated blood travels through systemic arteries and then into arterioles, and then the oxygenated blood travels into systemic capillary beds. As the blood travels through the systemic capillary beds, it becomes deoxygenated through the whole process that we just discussed, gives away lots of oxygen to the cells that lie around and within the capillary beds. And in doing so, the blood becomes deoxygenated. And what we end up with is deoxygenated blood within our systemic veins, which, as we'll discuss, are going to take the blood back to the right side of the heart so that it can be pumped to the pulmonary circuit and be reoxygenated. And we've already discussed, but let me say it one more time, what deoxygenated blood looks like. Once the blood has passed through a systemic capillary bed, the deoxygenated blood, the partial pressure of oxygen within the blood plasma within the deoxygenated blood will be 40. The partial pressure of oxygen within the intracellular fluid of the red blood cells will be 40. And inside of the red blood cells, the hemoglobin within the red blood cells will be 75% saturated with oxygen because they gave off 25% of their oxygen to the cells of the body. That was the whole point in reality of taking this oxygenated blood past our tissues, was for, yet again, the hemoglobin within the red blood cells to unload their oxygen so it could go into the cells. So now we have this deoxygenated blood, which actually should look kind of familiar because you saw it at the beginning of this lecture. And now where is this deoxygenated blood going to go as it travels through these systemic veins? Obviously, we need to reoxygenate or oxygenate this deoxygenated blood. How could we do that? So this is oxygenated blood traveling through a systemic artery into a systemic arterial, then traveling through a systemic capillary, going from being oxygenated to deoxygenated as the oxygen goes into the tissues of the body. And now this deoxygenated blood is going to enter into the veins. Right? And this deoxygenated blood is going to be carried by the systemic veins back to the right side of the heart. That's what defines a vein, a vessel that takes blood back to the heart. And in the systemic circuit, veins always carry deoxygenated blood. Right? They're carrying it back to the heart. And it goes into the right atrium, then the right ventricle, then it gets pumped into the pulmonary circuit. It gets pumped into the pulmonary arteries, which take the deoxygenated blood to the pulmonary arterioles, and then ultimately the pulmonary capillaries, and then the process repeats, right? From what we looked at before, the blood will get oxygenated at the lungs, right? This blood that was deoxygenated in the systemic circuit at the level of the tissues will be reoxygenated at the level of the lungs, right, in the pulmonary circuit. And now this oxygenated blood will travel through the pulmonary veins back to the left side of the heart and be pumped back out into the systemic circuit again. And this cycle, this loop will just keep repeating itself again and again and again and again and again endlessly for your entire life. So now I hope when you look at an image like this, which is showing how blood gets oxygenated at the lungs as it travels through a pulmonary capillary and goes past an alveolus, you can see how that blood became the way that it is, right? Deoxygenated blood has a partial pressure of oxygen of 40 within the plasma, a partial pressure of oxygen of 40 within the intracellular fluid of the red blood cell, and the hemoglobin within the red blood cell is 75% saturated. This is what you saw at the beginning of the lecture, and I didn't explain it to you how it was that way. But now you should realize how this happened. Deoxygenated blood is the way it is because of what happens as it goes past tissues in our body, as it travels through the capillaries of the systemic circuit. And that same deoxygenated blood is going to go past our lungs, past our alveoli, where the partial pressure of oxygen within the air in the alveoli is 100. And that is going to allow for the reoxygenation or the oxygenation of the blood, so that ultimately the partial pressure of oxygen within oxygenated blood will be 100 millimeters of mercury. The partial pressure of oxygen within the plasma of oxygenated blood will be 100 millimeters of mercury. In the intracellular fluid, the partial pressure of oxygen will be 100. Hemoglobin will be approximately 100% saturated with oxygen. And then that blood is, of course, going to be carried into the systemic circuit and go past the tissues of our body, where it will become deoxygenated and then brought back here again. So I hope this all, at least the bulk of it, makes some sense. In the next lecture, we will address how carbon dioxide is exchanged at the level of the lungs and the level of the tissues. We'll basically do this exact same thing, that we did with oxygen, except we'll do it with CO2 instead.